Okay, the general form for logs is y equals, then it's log of x minus h plus k. So I like to go through these first two at least because there's a bit of a difference. The one has the parentheses, and then that's x plus 1 in parentheses. That means that that plus 1 is with the x. So that's your h value. So the hk for this one would be -1, 0. So it's in parentheses. The h always comes out as opposite. The next one, where it's log base 4 of x plus 1, there's no parentheses. So it's like the x is essentially by itself. So then this one is, the h is 0 and the k is 1. So that's kind of the difference between those two. And then this one, the hk would be +2, -1. So h comes out as opposite, h is always with the x, k is on the outside, k is always the same sign. So to this slide, I also added, I wanted to add, like, how do you find the inverse function of these and how are they different? Because they look very similar. First, we have y equals log base 5 in parentheses x plus 1. And how do we find the inverse of that? And then how is that going to be different than without the parentheses? So the first step to finding the inverse is switching the x and y, because the inverse switches the input and output. So we'd rewrite this as x equals log base 5 of y plus 1. And then we could rewrite it in exponential form. So it would be, we want the log to be by itself before we rewrite it. So we have log base 5 of y plus 1 by itself. So then we'll rewrite it, and it would be base 5 to the x power equals y plus 1. So take your base, then you switch your input and your output when you rewrite it from log to exponential. Then you would finish solving for y by subtracting 1 on both sides. And we would get y, the inverse, equals 5 to the x minus 1. 5 to the x and minus 1, 5 and 1 there are not like terms, so I can't combine those. It doesn't become 4 to the x. It just stays like that. I wanted to do that one because I wanted to show you how it's different than if we don't have the parentheses. So log base 4 of x plus 1 without the parentheses now, and how is that going to look different for the inverse? We start the same way. To find the inverse, you switch around the x and y. So you get x equals log base 4 of y plus 1. But then before you can rewrite it in exponential form, you need to make sure the log is by itself. And this time the log is not by itself because it has a plus 1 at the end. That plus 1 is not with the y. So I have to do the minus 1 first. So we get x minus 1 equals log base 4 of y. Then I can rewrite it in exponential form. So then it's base 4 to the x minus 1 power equals y, or that's my inverse, my y inverse. So they're slightly different in HK, but they're also different in the way that their inverse works. So in the first one, the 1 was with the x, and then in the inverse, it's part of the y value. And then in the second one, the 1 was part of the y value, and now it's part of the x value. If that makes sense, I don't know. They were h's, now they're k's. They were k's, now they're h's. So that was like the biggest mistake that we saw in that I saw in the quiz from Friday too, was the inverse it was like the second one where you were supposed to subtract or add the 2 before you rewrote it as an exponent because it wasn't in parentheses. All right. Questions on that? All right, graphing. It's been a long time since we've graphed exponential function. So just to start as a reminder, the general form of exponential is a times b to the x minus h plus k. So I would start by identifying my shift then, which would be positive 1, negative 2. So you would take your h would be opposite up top, and then your k would be the same, so positive 1, negative 2. Once I have my shift graphed, then I would just graph the 4 times 1/2 to the x power. And I'm going to need an XY, AY column because I have an A and I'm plugging in X's, and then this is my A value is 4. So do you remember how to tell if this is growth or decay? It's decay because 1/2 is less than 1 and 1/2 is my base. I'm plugging in X's and I'm getting out Y's. So that reminds me that for this one I'm plugging in X values, and then I'm calculating the Y values by taking my base, which is 1/2, to my X power. So I would do that. I would do like 1/2 first to the negative 2 power, and I would get 2 over 1 to the positive 2 power, or 4. Then I would do 1/2 to the negative 1 power, and that would be 2 over 1 to the first, so 2. 1/2 to the 0 power, anything to the 0 power is 1. Then 1/2 to the first would be 1/2, and 1/2 squared would be 1/4. So these are always going to have reciprocals. The negative exponent outputs are going to be the reciprocal of the positive exponent outputs. And then the 0 power always has an output of 1. And that's whatever your B value is in the middle column. So our B was 1/2, so we took 1/2 to all of the X's. Then I'm going to multiply all of those middle columns by 4 because 4 is my number out front. If there is no number out front, like if it just was 1/2 to the X minus 1, then your A value is 1 and your base is 1/2. But this time I have to multiply all these middle numbers by 4. Or if it's a fraction, I'm going to multiply it by 4 over 1. 4 times 4 is 16, 2 times 4 is 8, 1 times 4. 1/2 times 4 over 1 would be 4 over 2, which is 2. And then 1/4 over 4 over 1 would be 1, 4 over 4. And then we cross out the middle column and we graph, but we have to graph from our shift, which I haven't graphed yet. So 1, negative 2 is to the right 1. Oops. To the right 1, and then down 2, and then graphing each of these points in the first and last column from this shift. So negative 2, 16 is way off my graph, but negative 1, 8, 0, 4, 1, 2, 2, 1. So all exponential decay functions should look like this shape. All exponential and log functions should have this general shape. So if you're not getting that nice curve, either the curve starts down and goes up, starts up and goes down. It could be the reciprocal of this, so it could look, starts from the bottom and goes back up, but they're all going to have that general curve. Domain are always your x-axis, or your x's, and range is always your y's. So you just need to try to remember, I plugged in x's. And I could pick any x that I wanted. I just chose those 5. So that means my domain is all real numbers for this one. And then my range is what has the restrictions to it. Because over on my graph, I can plug in any x that I want, but all of my y values are going to be above this dashed line. That's why when I drew this, I made sure I didn't cross that either. That's your asymptote. It goes through the y-axis, so the asymptote is a y equals. It was at negative 2. And all of my points, it opened up. All of my points were above negative 2 then for my range. Questions on graphing? Okay. So now graphing the log function. So again, the log function was log of base b of x minus h and then plus k. The first thing you're going to need to do is pick out the hk. Then you got to remember that if you have y equals log base b of x, then you can rewrite that as b to the y power equals x. So you would switch it around. So our shift for this one would be -1, -4. And then I would have to just graph y equals log base 3 of x now, which you would rewrite as base 3 to the y power equals x. So this time when you make an xy table, your inputs are y, because it's 3 to the y power. This part of the test is the no calculator part too. So you do need to be able to find 3 to the -2, 3 to the -1 without a calculator. But if you start with the positive exponents, that might be easier. So 3 to the 0 is 1, 3 to the first is 3, 3 squared is 9. If you can get those 3, the other ones are just reciprocals. If 3 to the first is 3, then 3 to the -1 is the 1/3. And 3 to the -2 then would be 1/9. So those are the reciprocals of those. In Algebra 2, we don't look at log functions with any A transformations, so we don't need a third column for this one. And then you're going to graph it from your shifted point just like we did with the exponential. But remember, it's x, y, so you're going to go over 1/9 down 2 because x moves it right and left, y coordinates go up and down. So you got to go 1/9, which is just 0.1 over down 2. Then 1/3 over down 1. Over 1 up 0. Over 3 up 1. Over 9 up 2. And then it's going to follow this vertical line but not cross it. This time that vertical line is your asymptote. Since the line that doesn't cross it, it goes through the x-axis, your asymptote is an x equals. It's a vertical line. It's x equals -1. Your domain is all your x's and your y's. Or domain is x's and range is y's. But this time I picked all my y values, so that's why y is all real numbers. Y was my input, and I can plug anything into that function, 3 to the y power. But my output, my x values are restricted. All my x values are greater than that -1, which I can see on my picture too. So the asymptote for this one is always x equals h, and the domain is always x greater than whatever your h value was. In the previous ones, it was y equals k. And then it could be greater than or less than for exponential because it depends on if it opened up or down for a range. Questions on that? All right. So this goes along with the no calculator part of the exam as well. I'm asking for exact answers. And how to do this is you have to set it up as an equation, so set it equal to x. And then you're going to use the idea that if you know that you have a log base b of y and it equals x, then you know that b to x power has to equal y. So this is probably the most important thing to know tomorrow for the test, is to be able to go back and forth between these two. In order to graph a log, you have to write it as an exponential. In order to solve these, you have to write them as exponential. In order to solve other equations, you have to either write it as exponential or take an exponential and write it as a log. So going back and forth is going to be really helpful. So this one would be base 9, and then your input and output switch. So it's going to be to the x power equals 1 over 81. Then you have to try to figure that out. 9 to what power equals 81? 9 times 9 is 81, so 9 squared. So to get a fraction, it would be -2 then, because 9 to the -2 power would be the same thing as 1 over 9 squared. So if you start with a whole number and it ends as a fraction, that means your exponent has to be negative. This one's equal to 2 because 5 squared is 25. So the base to the answer gives you what's inside. If you start with a larger base, like base 27, it's to power that equals 3. So base of 27 to the x power equals 3. Then you have to think of fractional exponents. So what root? How many 3's does it take to make 27? 3. So that means it's the cubed root of 27 equals 3, and the cubed root is the same thing as the 1/3 power. So that one would equal 1/3. The last one here is the natural log. The natural log, you have to remember that it has a base of e. So I like to remember that it goes together in the calculator. E to the x and ln go together, just like base log is base 10 and it goes with 10 to the x on the calculator. So this is like base e. So if I rewrote it, it would be e to the x equals 1 over e to the -7th. And I have the bases are the same here, so now I can set the exponents equal, except for they have to have, I guess they're not quite the same yet. E to the x equals 1 over e to the -7th is the same thing as e to the +7th over 1. So then the bases are the same, so the exponents are equal. So x equals 7. Okay, so solve, check for extraneous solutions when necessary. So extraneous solutions exist when you can't evaluate a log of a negative number. And this is why you can't do that. So if I said log of 2 base 2 of 8 equals 3, because I know that 2 cubed equals 8, right? That's how that works. 2 to the 3rd equals 8. But if I said log base 2 of -8 equals x, this is not possible, because if I rewrote this one in exponential form, it'd be 2 to what power gives me a negative number. And I could have made that negative number in there any number. -10, -12, -15. It doesn't matter. It can't happen. There is no exponent that you could plug into this to get a negative output. If I plugged in 2 to the -2 power, it would be 1/4. 2 to the 0 power is 1. 2 to the 2nd power is 4. So you will never get 0 and you will never get a negative answer. So that's why it's not possible. That's why you can't take the log of a negative number. So you have to check for extraneous solutions anytime this happens. Anytime when you plug it back in and you get a log of something negative, that's no solution. Can't have that. The log itself can equal a negative output, but it can't take in a negative input. But if you are given a log base b of y equals x, then you have two options. Either you rewrite it as x equals, and you use change of base, log of y over log of b, or you rewrite it in exponential form, where you write b to the x equals y. Sometimes you'll be able to solve when you go from log to exponential and solve for b. If not, then you need to change a base formula and say, if you have a log base b of y, you can solve that log by doing the log of y over the log of b. So this one is base x, so it'd be x squared, x to the second power equals 81. So then I know x would equal 9. X here represents the base of the log, which is b. So b has to be positive. It's never negative. So I don't need plus or minus here. It's just x equals 9. This one would be 9 to the x power equals 3. And can you figure that out? Close, 1/2. Because the square root of 9 equals 3. So it'd be x equals 1/2. If this was on the calculator part and you were struggling with that, you could also do the change of base. You could say that x would equal, it would be the log of 3 over the log of 9, because it's the log of y over log of b. And if you type that into your calculator, then if you did log of 3 divided by the log of 9, it would give you 1/2, 0.5. So that's where you can use the change of base formula. But if that question's not on the calculator part, then you have to know that the square root of 9 is 3, so it's 1/2 power. I skipped the one up there to the right, but that's because it's similar to this one here, where I have 5 to the 2 to the 2x minus 1 power equals 125. And I know that 125 is the same thing as 5 cubed. So I could rewrite this like this. And then the bases are the same, so I can set the exponents equal. And then I would solve for x. Now, I don't have to worry about extraneous solutions for exponential functions because you can plug in anything you want there. There's also one where, like, if you have log of any base and it has, something, and it's equal to log of the same base of something else, then that means that whatever's inside has to be equal to. So that's kind of the same idea. If the bases are the same, you set what's in the exponent or what's inside equal to each other. So if you have 2 logs equal, you can set the insides equal as well and then finish solving. But if you're given a log and you need to solve it, then you need to first get the log by itself. Then you need to divide. So that you get the log all by itself. So that minus 5 was on the outside. It wasn't in parentheses, so I had to add it first. Then I divide by 3. Then, once you have the log by itself and you're trying to solve, you're going to rewrite it in exponential form. So this is base 2 to the 4th power would equal my x. And so then x would be 16. If I plug that back in, I would have 3 log of 2 of 16 minus 5. That's fine, because I have log of positive 16. If it was plugged back in and I got log of a negative number, it would be no solution, extraneous. Let me see what else. These are probably good ones to do. going the other way. So I'm starting with exponential, which means I have the x and the exponent. So get the piece with the x and the exponent by itself first. So here I would have to subtract 2. I would get 5 times e to the x equals 15. I would have to divide by 5. I get e to the x equals 3. Then you need to change it back to log. So if you have b to the x equals y, then that's log base b of y equals x. It's the same thing I've written a few times. So this would be log base e, and then you would take log base e of 3 equals x. But what is log base e of 3? What is log base e? It's the natural log. So log base e is actually the ln. So this is actually the ln of 3. So that's what you would use to plug into your calculator. You would take the natural log of 3. I suppose you could do log of 3 over log of e. You'd get the same answer, but not necessary. Natural log of 3. So x is approximately equal to 1.098 would be 1.10. This one, you'd get the x plus 3 by itself, so you would add 5. That plus 3 is going to stay up there with that exponent, though. So you're going to get 9 equals 2 to the x plus 3 power. Then you're going to rewrite it in log form. So right now, 9 is your output, and 2 is your base. X plus 3 is your input. So when you rewrite it, it's going to be log base 2. 9 is going to be your input now, and x plus 3 is going to be your output. They flip-flop when you rewrite it from exponential to log. Then log base 2 of 9 is 2 to what power equals 9? If you can't solve that in your head, then you need to use the change of base. So there's nothing, 2 to the third is 8, but nothing to the power is 9. So that means this is a decimal answer. So you use change of base here. It's going to be log of 9 divided by log of 2. That way we can get that decimal. Then we subtract 3. So my exact answer is log of 9 divided by log of 2 minus 3. And in my calculator, that would be, log of 9 divided by log of 2 equals minus 3.17. And the test asks you to round these to 2 decimal places, so that's what I'm looking for. I looked at the test this morning, and these are actually not on it. So probably because we already assessed you on that in a previous unit, plus we're doing it in the next unit. So it's not that you have to forget how to do that, but we're going to do that again later. I talked about inverse functions once before, but we can practice it one more time. So you switch, and the test asks you to round these to 2 decimal places, so that's what I'm looking for. I looked at the test this morning, and these are actually not on it. So probably because we are x, and then it would be equal 3y. So your input and output would switch. You would switch from e to the 3y, would become ln of x equals 3y. Then you would finish solving for y by dividing by 3. So here my inverse would be the ln of x over 3. That's pretty much it, except for like growth, decay, interest equations. So I can just run through when you use which equation for which problems real quick. And then you'll still have a little bit of time. So this one, these two here are both for interest. These two. This one is for if it's compounded continuously, which is my first example, compounded continuously. This one is where it's compounded like monthly, yearly, weekly, etc. And then your n value would change. So like if it's compounded monthly, you would plug in n equals 12. Yearly, you would plug in n equals 1. Weekly, you would plug in n equals 52. Like on the quiz, I think it was daily, then you plug in n equals 365. So those two equations are for interest problems only. If it deals with any sort of interest that you are earning or paying, those are the equations that you use. And then it depends on the number of times it is compounding. Otherwise, you plug it into the formula and you're good to go. The other two are exponential growth or decay. This one is growth. This one is decay. So keywords for this one would be like something is increasing. This is like decreasing. It could still be money, but it would be worded differently. It would say like the value of your car is decreasing at 3% rate per year. So it's not saying that the interest in your car loan is decreasing. It's saying that the value is decreasing or the value is increasing. Then you use those two equations instead. And that's the rest of the problems. Do you want me to plug in one of these and see how it's plugged in, or are we good with that? And give you some time to work a little bit. Oh, okay, sounds good. Thank you.